get started.
Okay, so pardon me. Today I'm going to do a presentation about how we can leverage computer vision to encode time series data as images to use in traditionally visual recognition algorithms. So the structure, I'll be going through the background, just a brief overview of computer vision, the Gramian Matrix, the Gramian Difference Field and Gramian Summation Field, motivation from a multi-channel solution to visual recognition, a Markov Transition Field, and then further implementation. So the past few decades have shown immense importance in applying deep learning methods to time series data to solve real-world issues. However, traditional numerical methods in forecasting both univariate and multivariate time series have proven to be difficult due to their problematic features, including the inability to preserve temporal correlation, lack of pre-trained models, and difficulty in training RNN models. Traditional models also tend to act erroneously when presented with multiple input variables and incorrectly pre-process time series data. So this has posed the question: how can we leverage existing, less common techniques that are used in machine learning to improve our predictive performance on time series data? So inspired by recent successes of supervised and unsupervised learning techniques in computer vision, we consider the problem of encoding time series as images to allow machines to visually recognize and classify and learn structures and patterns. By leveraging the techniques of computer vision, the hypothesis is that we will be able to apply common deep learning algorithms, such as CNN, to their full performance capacity. So the specific boom in computer vision has reimagined the way we analyze time series. This concept of reformulating features of time series data as visual clues already has been explored by data scientists, with revolutionary improvements having been made in the past decade. So I guess the first really revolution was in 1990 when Hermansky proposed a method of concatenating MEL frequency spectral coefficients to transform speech data into an image. In 2010, another algorithm was posed where recurrence networks are used to analyze structural properties of time series data from complex systems by building adjacency matrices from recurrence functions to interpret the time series as complex networks. And then a year later, in 2011, Kimpenharo proposed building adjacency matrices by extracting transition dynamics from the first order Markov matrix. So that proposal in 2011 is actually relevant to our presentation today. So these complex visual models all successfully present different topological properties amongst different time series. So they do maintain the spatial relationships of data by representing spatial objects as an underlying graph of topological primitives, being nodes, faces, and edges. However, these models that have been created in the past fail to maintain a relationship to the original time series data for lack of exact inverse operations. Thus, the problem becomes finding an acceptable method to reformat time series data as visual clues, whilst maintaining a relationship with the original time series data, the exact inverse operation. So in 2015, a very novel approach and representation for encoding time series data as images was postulated by Tim Oates and, I can't pronounce the name, Wang, and this representation sought to address the above issues. So this representation is called the Gramian Angular Field, GAF for short. The GAF is a representation that was developed from the concept of a Gramian matrix. This matrix is already used in common property of machine learning in problems including image style transfer, which I'll explain in a bit. And therefore, to understand how the GAF representation works, we really must first assess and analyze the Gram matrix. So in linear algebra, given a set of n vectors, the Gram matrix is the matrix of all possible inner products of X under the assumption that the data exists on a finite dimensional Euclidean space. So just some context and some background, the basic properties for an inner or dot product, they are the same when they're in a finite dimensional Euclidean space, are that the dot product can be written as A, B cos theta, and then the closer the vectors are to each other and the more similar, the smaller the angle becomes. As theta decreases, cos theta increases. Therefore, the closer two vectors are together, the greater their dot product. So intuitively, a dot product can really be seen as to how similar two vectors are. This is important later. So as mentioned, the Gramian matrix has already been involved in problems such as the image style transfer application. So the neural style transfer in machine learning problem is where we compose one image in the style of another image. So in this problem, we generate content, so in this case, our dog, and generate our style, in this case, Kandinsky, to produce a final output of the generated content in the generated style. So again, in this case, it's the image of the dog in the style of Kandinsky. So to generate content, it has already been proven that convolutional feature maps are a good representation of the input images features. They do capture spatial information of an image without containing the style information. On the other hand, to generate style, it has already been shown that a Gram matrix is a good method to generate the style of an image. So if we consider two feature vectors, more specifically two flattened feature vectors from a convolutional feature map of depth C, representing features of the input space, their dot product gives us information about the relation between them. So as mentioned before, the basic properties of a dot product, the less of the product, the more different the learned features are, and the greater the product, the more correlated the features are. In other words, the less of the product, the less of the two features co-occur, and the greater it is, the more they occur together. So this obviously gives us information about an image's style, and this whole property is relevant in the GASF. So Oates and Wang used this unique application of the Gram matrix in image style transfer and developed it to be applicable to time series. The motivation was to create a Gram matrix that highlighted the correlation between each set of observations to further be used in prediction. However, the Gram matrix calculates the inner products of vectors in a 2D space, that is, a space that can be defined by the x and the y axis. Therefore, a method of pre-processing must be applied to transform the 1D univariate time series data from the original Cartesian space. So to do so, the time series must first be mapped by a polar ordinate system, where each point on the plane is determined by a distance from a reference point and an angle from a reference direction. This is imperative for calculating the Gram matrix. So as previously mentioned, a key property that this method must have, is that it must have an exact inverse operation to ensure that the transformed data can be reverted back to the original and raw time series format. So as you can see by the image below, it sort of shows how we can transform, not how we can transform, but the different shape between the original time series data and the polar encoding of the exact same data. So to represent the Cartesian time series data in a polar coordinate system, an inverse cosine function is used. In this polar system, both the time series data value and the corresponding timestamp need to be accounted for. These values following transformation will represent the angle and the radius of the polar coordinate, respectively, with the equation below. So phi is obviously the inverse cosine of each observation x, and then the radius is a timestamp divided by n, a constant factor, to regularize the span of the polar coordinate system. However, again, we mentioned and we go back to the concept of the exact inverse operation. So for the previous transformation to actually be bijective, and therefore only have one single inverse value, restrictions must be imposed on the data. To reiterate, the Gram matrix calculates the cosine of the angle between each set of vectors. For this calculation to be bijective, cos phi must be monotonic, and this property is satisfied only when phi is an element of 0 and pi. Between 0 and pi. So for this to be satisfied, the original time series must be normalized before transformation. So time series x must be rescaled so that all values fall in the interval between -1 and 1. So the proposed method by the people who proposed this algorithm is as below. So each observation xi is taken by that observation minus the maximum value of the time series x, plus, again, the observation minus the minimum value, and then over the maximum value minus the minimum value. So just relating back to the afterpay example that I've used in multiple algorithms before, after scaling the data and using the inverse cosine to invert into a polar coordinate system, the data will look like this. So the first column is the original, the second column is the scaled, and the third column is the close price, where the close price is expressed in a polar coordinate system and, is expressed in radian units in the polar coordinate system. So the polar coordinate-based representation is actually a novel way to understand time series and has two very important properties that I've mentioned before. So again, it is bijective as cos phi is monotonic, Given a time series, the proposed map produces one and only one result in a polar coordinate system with a unique inverse map, allowing us to reproduce the original raw time series data. And the second property is that opposed to Cartesian coordinates, polar coordinates preserve absolute temporal relations. So this preservation of temporal dependencies is due to the properties of the Gram matrix. Since time increases as a position moves from top left to bottom right of the matrix, the time dimension is encoded into the geometry of the matrix. So again, we mentioned that the top left will be the observation I and observation I plus 1, whereas the bottom right will be observation I and observation N, where N is the furthest from I. So now that we've transformed the data into a polar coordinate system, we can exploit the angular properties of the values and properties of a Gram matrix to highlight the correlation between data points. As we mentioned before in the image style transfer, the value of the individual elements of the Gram matrices will show how correlated the points are. So again, the Gram matrix is the inner product of each set of vectors. And in this exact problem, assuming that all 2D vectors are of norm 1, this translates to a matrix where each element is the cos of an angle, that is the angle between vectors I and j. However, the inner product in a 2D polar space does have some limitations, as the norm of each vector has been adjusted for the time dependency. So the two properties we should acknowledge is that an inner product between two distinct observations will be biased in the favor of the most recent observation as the norm increases with time. When computing the inner product of an observation with itself, the resulting norm will also be biased. So to account for these two properties, two alternative operations are proposed by considering the trigonometric sum difference between each point to identify the temporal correlation within different time intervals. So the two different operations are the Gramian Angular Summation Field and the Gramian Angular Difference Field, where the former is the cos summation of angles and the latter is the sine difference of angles. So again, we should also mention that these operations can be converted back into an expression of Cartesian coordinates, thus the original time series data can be achieved. So the resulting Gramian Angular Summation Field matrix with the transformation can be expressed as the matrix of cos angle summations, and the matrix expansion, the matrix definition, I guess, of this is as below. And so then by defining the inner product as x dot product y minus square root of 1 minus x squared dot product square root of 1 minus y squared, the above actually is a quasi-Gram matrix. Similarly, the Gramian Angular Difference Field with the transformation can also be expressed as a matrix where each element is assigned difference of angles. Again, this can be defined in matrix formation, and again, this is also representative of a quasi-Gram matrix. So, as the final pre-processed Gramian Angular Summation Field and Gramian Angular Difference Field matrices are each quasi-Gram matrices, they do resolve all properties of the Gram matrix that were mentioned previously, focusing on the correlation pattern and the temporal dependency between observations. So, both imaging algorithms individually have been postulated as an appropriate mechanism to leverage computer vision in time series prediction. These techniques allow for time series data to be converted into images to be used as input for traditional visual algorithms such as CNN and extensions of the architecture such as ResNet. Again, they preserve temporal dependencies and can take full advantage of visual algorithms. So this is an example, again, using the Afterpay data. A Gramian Angular Summation Field and a Gramian Angular Difference Field has been applied to the whole data. So as you can see, there are 899 observations. This is the image size is 899 by 899. And these are the images created that we would push into further deep learning architectures. So whilst the image encoding of time series data is a novel approach, a more complex architecture is proposed that consists of a multi-channel image rather than a single image created on a 1D dataset. So looking back at these images, Whilst we have created an image for the data set, it should be noted that this may not be effective in algorithms, because whilst it does capture necessary information about the time series, it is more relevant to identify correlations between days close to each other, rather than in these examples where ultimately we are identifying the correlation between days that are, for example, 300 days away from each other, which is obviously not intuitive in financial time series. So again, this idea of a multi-channel image has been proposed where it attempts to capture more information about the data. So the multi-channel image attempts to, again, capture the information assessed by both the Gramian Angular Summation Field and the Gramian Angular Difference Field, as well as another computer vision technique. So the additional computer vision technique is an extension to the algorithm mentioned before, proposed by Kemp and Haro, where adjacency matrices are built by extracting transition dynamics from first-order Markov matrices. So this technique is called the Markov Transition Field and is used as a visualization algorithm to assess the behavior of time series. So as in the Gramian Angular fields, the motivation between the Markov Transition Field is to preserve temporal and frequency correlation dependencies embedded in time series data. Thus, the Markov Transition Field must encode dynamical frequency information in the temporal ordering incrementally. So the Markov Transition Field is based on the concept of a Markov matrix, a square matrix that is used to describe the transitions of a Markov chain. The matrix describes the probability of moving from one state to another in a dynamic system. As prior, this method of data visualization has an exact natural inverse, satisfying the limitations of current computer vision techniques in time series data. So to create a Markov transition matrix from time series data, the data must first be discretized along the different values you can take. So given a time series X, the values are discretized into Q bins, and this is the most common way to achieve quantized dictionary. So each observation Xi is actually mapped to a bin Qj, and after each observation is mapped to the corresponding bin, Q by Q weighted adjacency matrix W is constructed by counting transitions among bins in the matter of a first order Markov chain along each time step. In matrix W, each element Wij is given by the frequency with which a point in the quantile Qj is followed by a point in the quantile Qi. So by nature, the previous Markov transition matrix is actually insensitive to the distribution and temporal dependencies of time steps Ti. However, again, we'll mention, if temporal dependencies are not captured in the imaging algorithm, too much information is lost from matrix W. Therefore, an alternative definition, the Markov transition field is formed, which extends the Markov transition matrix. As a high-level overview, the Markov transition field extends the Markov transition matrix by assigning the probability from each quantile at time step I to the quantile at time step j at each element Mij of the Markov transition field. In this way, the Markov transition field therefore encodes the multi-span transition probabilities of the time series. Also, the main diagonal in the Markov transition field, as in past Gramian Angular fields, captures the self-transition probability at time step I, making the algorithm reproducible. So a key problem, or limitation I should say, of the Markov transition field is the actual size of the image. So to make the size more manageable, it is reduced by averaging pixels in each non-overlapping square patch with a mathematical blurring kernel. And then from this Markov transition representation that has been blurred, we have an aggregate of the transition probabilities in each subsequence. So in this image, this isn't our data, this is just an example. You can see how the time series has been transformed into a matrix showcasing the transition probabilities, and then how that has been turned into a Markov transition field. And then using the blurring kernel, how have we made the size of the image a little bit more manageable. So after all this, we now have three imaging algorithms: Gramian Angular Summation Field, Gramian Angular Difference Field, and the Markov Transition Field. So it actually has been proposed to concatenate all these three imaging algorithms into a multi-channel image to leverage the advanced prediction performance and capture the granularity of the information within the time series. So this concatenation has also allowed for a multivariate time series analysis, which is often imperative for accurate data prediction. And it should also be noted that just simply using a granular Gramian Angular Field is not possible in multivariate time series analysis. So by the image below, you can see how a multi-channel image can be, stacked together in an ensemble to be pushed through a classic CNN LSTM algorithm that we have used many times before. So again, we use the R2P example. In this example, we have used the, we use the same labeling technique as in our original models. So that is, we take the first 10 days as features and the 11th day as a label. So in this way, each GASF, GADF, and MTF representing these observations are created. So each observation shows the movement, correlation, and transitional probabilities of 10 days. So the first row is day 1 to 9, the second is day 10 to 19, the third is day 20 to 29, and so on. So as you can see, the first image of each row is the movement of the time series in those 10 days. The next is the summation field, then difference field, and transition field. They all show different properties, so it is imperative and beneficial for us to be able to stack and concatenate these images to create a multi-channel image to be used in further algorithms. So after all this, further implementation to this algorithm can be to leverage the multi-channel nature of this algorithm. We can create and concatenate more sophisticated images. So in this case, we'll be concatenating technical indicators, fundamental analysis, and risk metrics. So again, to expand the previous image we used of multi-channel imaging, when we pre-process our data, we can create technical indicators. So for example, moving average, RSI, anything that we feel is relevant in the domain of our data. And we can use those as part of our multi-channel image as well. And then we can again push this stack through a classic visual recognition algorithm. So to continue again, in the original GASF algorithm proposal, the radius is actually omitted from the final calculation of the GASF and the GADF matrices. So this radius may actually capture important information about the raw time series data. Therefore, it should be hypothesized whether omitting this radius is causing a decrease in predictive performance. And finally, many deep learning algorithms that have been already successful in predicting time series data are fundamentally image recognition algorithms that actually do convert numerical data into images automatically. So we should conduct evaluation into whether manually converting time series data into images should be conducted. And that's it. Thank you.